So this next topic does build on something that we've already done earlier tonight. Hope you see a chance to figure out what that is in a minute. It's looking at two different types of indeterminate forms. So remember that in week 2, we did several examples where we had a fraction where both the top and the bottom of the fraction were going to infinity. And what we figured out then was that this is a fraction that is called an indeterminate form, because unlike most fractions, like 12 over 3, if you have the top of the fraction going to 12 and the bottom going to 3, the answer is always 4. There's no doubt about that. But when you have the top and the bottom both going to infinity, or one of them going to negative infinity, or both going to negative infinity, the answer can be any real number, or it can be infinity, or it can be negative infinity. I think in week 2, we saw an example where the answer was 6, for example, 6, because that was somebody's favorite number. We also saw 0. We also saw infinity. Similarly, there's the indeterminate form where the top and the bottom of the fraction are both going to 0. And in fact, almost every time that we use the limit definition of the derivative, where we have h going to 0, both the top of the fraction and the bottom of the fraction there are going to 0. The only time that it's not, of course, the bottom is always going to 0 because h is going to 0 there. Sometimes on the top, if you had a discontinuity in the function, the top might be going to some non-zero number, in which case the derivative would fail to exist at that point. But as we know, also there, every time that we take a derivative, we don't get the same answer, right? It's not always 1. So when we have one quantity going to 0 over another quantity going to 0, the answer can also be any real number, or plus or minus infinity, or it can even fail to exist. The examples that we did in week 2, I made them up with some easy algebra solutions, and we didn't need to use anything fancy at all to evaluate those limits when we had infinity over infinity. But in many cases, we do. So for example, if we have something like the limit as x goes to 3 of e to the 8x minus 24 minus 1 over 2x minus 6. This is the one that you're going to explore in an applet in a minute. As x goes to 3, this thing on the top here goes to e to the 0, which is 1. So we have 1 minus 1, which is 0 on the top. And on the bottom, we have 6 minus 6. So the top and the bottom are both going to 0. But you can see there's no nice, easy algebraic solution to this because there's nothing that we can cancel out or simplify like we did in week 2. Calculus, though, will come to the rescue and help us evaluate this sort of limit. So that's what we'd like to do now. We'd like a way to evaluate these two indeterminate forms, the infinity over infinity and 0 over 0 forms, when algebra itself doesn't do the trick for us. By the way, our usual historical aside, the phrase indeterminate form was first used by a French priest, an amateur mathematician. I don't know how you pronounce his name, but this is how you spell it, back in 1840. So we have an applet for you now to explore this indeterminate form. So please go ahead and try that applet and see if you can come up with some idea about how the ratio of the fraction of the numerator and the denominator of the fraction relates to something that uses derivatives.